Bismillah ar-Rahman ar-Rahim. This is another example related to uniform circular motion. It is related to what we call the roller coaster. You might have seen this in the amusement park roller coaster, where you have passenger's car moving up the hill, down, then it goes in several acrobatic ways for entertainment. The fully loaded car, just let us make it simple. The mass is 1,000 kilograms. The radius of all of these curves, they are circular and they have radius of 100 meters. So this is 100 meter, 100, and there also it is 100 meters. The speed of the car at point A is the same as the speed of the car at point B. So this is A, that is B, and it is 10 meters per second. Okay. Here in this part, point C will have a different speed, which is 40 meters per second. In this question, would like to find the normal force on the car at point A. So the normal force, which is the push of the road or the track on the car at point A. Then find the normal force on the car at point B. Then would like to have other questions. Let us start with part A. In part A, as it is always the case, we should start with the application of Newton's second law. We should apply Newton's second law on our situation. Okay, and the first step is to draw the free body diagram. Okay, so part A, we draw the free body diagram. So this is my car. Okay, this is the road. The road is here. Okay, what are the forces? We have Fg downward, and this is the surface. So the surface is pushing our car vertically upward. This is the normal force. Any other forces? We don't have other forces. Then where is the acceleration? Is there acceleration here? Yes, there is centripetal acceleration, because this is circular motion. So the acceleration is toward the center, and the center is downward, down the car. Okay, so this is our AC. Okay, I have the forces and I have the acceleration toward the center. Why did I draw the acceleration downward? Because the car is at the top of the hill. Where is the center of the circular path? It is here. So the acceleration, in fact, is toward the center. From its name, it is centripetal acceleration. Okay, it is time to apply Newton's second law. Let us apply it. Okay, the general form F net equals ma. In this case, this acceleration is centripetal acceleration. What are the forces? I'll use this convention. This is my positive y axis. So anything upward will be positive. So I have Fn positive because it is upward. Fg is downward. So it is mg minus because it is downward, equals. Now, the acceleration is downward according to my choice here. This should be minus m AC, which is v square over r. Okay, we are interested in finding the normal force. So Fn equals, this will go to the other side with a positive sign. So this is mg minus v square over r. Okay, mass is a common factor, and I plug in the numbers. So this is 1,000 kilograms, the mass of the car, 9.8 minus v square, which is 10 squared, 100, divided by the radius, which is 100. So this is basically 1. 9.8 minus 1 is just 8.8. 8.8 multiplied by 1,000. This will give us 880 newtons. This is Fn at point A. It will be 8,800. Okay, one more newtons. Okay, let us proceed to part B. In part B, we will have the car is at point B and would like to find what is the normal force there. We draw the free body diagram. So this is my car. It is now at the bottom. Okay, so the center is somewhere here. Okay, and Fg is always downward. So this is Fg. Okay, the normal force, the surface is pushing my car upward. Okay, so the normal force is upward. So this is Fn. And what is remaining? Remaining the acceleration. What is the direction of the acceleration? It is towards center. Where is the center? The center is now on the top of the car. So it is upward. Okay, so this is AC in this direction. Now I am ready to apply Newton's second law. Newton's second law says that F net equals ma. This is in general, but the acceleration in this case is centripetal acceleration. I'll use the same convention. Anything upward will be positive. Okay, so Fn is upward, positive, minus mg equals AC is upward, so in this case it will be positive, mv square over r. And I am left with Fn equals mg plus v square over r. Okay, plugging in the numbers. So this will be 1,000 multiplied by 9.8 plus 10 squared, which is 100, divided by 100, which is 1 plus 9.8. So this will be 10.8 multiplied by 1,000. So this will give us 10,800 newtons. And this is Fn at point B. Notice one thing, that the normal force at point B is greater than the normal force at point A. As you might have experienced this in your car or in the roller coaster if you have gone to the park one day. Okay, so at the bottom you feel too much push from the seat of the car on you, and the same also applies to the push of the track on the car. And this is larger than being at the top of the hill, like point A here. Okay, let us now, and you feel yourself as if you are, want to fly at the top there. But here at the bottom, you feel too much pressure on your back. Let us now proceed to point C. Part C. Find the maximum safe speed with which the car doesn't leave the track at point A. You see, as long as the car is in contact with the track, you are in a safe situation and there is no problem. But as you increase the speed, what will happen? You will reach to a point where the car would like to leave the track. Leaving the track means that there is no push from the track on the car. What does it imply? It implies that the normal force in that case will be zero. So here, he's asking about the situation when the normal force is equal to zero. Okay? And this will happen at point A. So at point A, okay, so I'll go answer part C. Okay? We know that at point A, we know that the normal force, as we can see there, the normal force equals m multiplied by g minus v square over r. Okay? As long as this normal force is positive number, the car is safe, but the problem will happen when the normal force equals to zero. Okay, so we have to equate this equal to zero to leave the track. Normal force equals zero means the car is almost leaving the track and there is no touch between the car and the track. Okay, so mass multiplied by this much equal to zero. The mass cannot be zero, so this much is equal to zero. So this implies that g minus v square over r equals to zero. And from here, we can find that v equals R multiplied by G under the square root, and this is V max safe. If we plug in the numbers, this is 100 multiplied by 9.8, so this is 980 under the square root. This is 31.3 meter per second. This is the maximum safe speed. So if the car is moving at point A with a speed of 10 meter per second, you are in good shape. 20, 25 up. But if you decide to drive at a speed of, say, 35, at this point, the car will fly off, okay, and it will leave the track at that moment. Okay, let us continue the fun. Part D, find the normal force on the car at point C. Here, at that location, you will be upside down, okay? You see the wheels of the car at the top, and your head will be toward the bottom, okay? And would like to know what is the normal force there, where the speed at that point is equal to 40 meter per second, okay? So the speed here was 10, here the speed was 10, but now at this point they started increasing the speed. At that point, the speed is 40 meter per second, okay? Let us draw the free body diagram. So this is part D. Free body diagram, so this is my car. These are the wheels of the car. The gravitational force is always downward, Fg, okay? Where is the normal force? The normal force is the push of the track on the car. Where is the track? The track right now is here, okay? This is the track. So the push of the track will be in this direction, okay? So this is Fn, okay. What is the other force? No other force. Do we have acceleration? Yes, because of the circular path, so we have centripetal acceleration. It is toward the center. Where is the center? The center is downward, okay, with respect to the car. So AC is in this direction, okay? Let us choose, as usual, this is the positive Y direction, and we apply Newton's second law. F net equals MA, okay? This is the normal, the general form of Newton's second law. What are the forces? I have Fn downward, Fg downward, and the acceleration is downward, okay? So I have minus Fn minus Fg, which is mg, equals minus mv square over r. You see minus, minus, minus. You can multiply the whole equation with a minus sign, so you are left with plus, 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 okay? And here we have Fn at that point will be equal to m v square over r minus g. Okay, so this is the normal force at point C. So the mass here is 1,000 kilograms. The speed is 40 multiplied by 40, so this 1600 divided by 100 minus 9.8, and we are left with the normal force, which is equal to 6,200 newtons. 6,200 newtons. That is the normal force at point C. Okay, good. Now, you might think of there might be a problem with this car at point C if we have reduced the speed. If we reduce the speed a little bit, you can look at this equation. If we reduce the speed, what will happen to this quantity will be reduced. Okay, reduce until the normal force becomes equal to 0. When the normal force equal to 0, what will happen? The car will lose contact with the track. Okay, okay. So we would like to calculate it. Find the minimum safe speed for the car not to leave the track at point C. This is what we want, actually. The designer of the car and the operator of this roller coaster, he should be careful about these calculations, okay? So we'd like to find what is the safe speed. This is part E. Okay, for V minimum, we know that Fn at that point C, is given by this. So Fn equals m multiplied by V square over R minus G. Okay, for this car to lose the track, this should be equal to 0. So I have the multiplication of this amount with this much equal to 0. It means one of them can be 0 or should be 0. This cannot be 0. So we are left with V square over R minus G equals 0. And from here we find that V equals the square root of R G. So this is V minimum at point C. And this will give us 31.3 meter per second as the minimum safe speed to pass point C safely. I hope with this example you have comprehensive idea about the application of Newton's second law for the case of uniform circular motion, especially for this type of problem, which is related to the roller coaster. So now we have applied, as you can see, this very comprehensive example. We have applied Newton's second law along the radial direction. Okay, so we applied F net equals MAC. Okay, because my forces and the acceleration are along this radial direction. There might be forces along the horizontal axis. Okay, but we are talking about uniform circular motion. It means there is no acceleration. Okay, there might be forces which cancel each other, or maybe there are other forces which do not cancel each other, but we are not interested in that. We are interested in the forces along the vertical axis, which is the radial direction in our problem. Thank you.